Okay, let me start class.
Hello students, right now I'm going to tell about the discussion of the homework. Yesterday you got homework about drawing dot and cross diagrams for the following compounds or molecules. From number 1 until number 5, this one, if you draw covalently it would be incorrect because all this number 1 from number 5 is between metal and non-metal. Let's see here. This is sodium with chlorine. Sodium is metal, chlorine is non-metal. Also magnesium, metal, chlorine is non-metal. Sodium, metal, oxygen is non-metal, and also the last is magnesium, metal, oxygen is non-metal. So if we have to draw like this. Sodium has lost its outermost electron. The one electron has been transferred to the chlorine. So because sodium lost one electron, it carries one positive charge. And then the chlorine gains one electron, so it has one negative charge. And then magnesium chloride, MgCl2, magnesium has lost its outermost two electrons. That's why the electron here, we draw the outermost shell, it is empty. It carries 2 plus. The electrons go to the 2 chlorine atoms. So one chlorine will get one electron from magnesium. There are 2 chlorine atoms. And then with sodium require 2 sodium atoms and 1 oxygen atoms because 1 oxygen atoms requires 2 electrons. So the electron comes from the sodium atom. So these 2 sodium will carry 2 positive charge. Each sodium will carry 1 positive charge, so total 2 positive charge. And then with magnesium oxide, it will be the same as sodium chloride, magnesium chloride, sodium oxide. Magnesium will lose 2 electrons in the outermost shell, transfer to the oxygen. One oxygen gains 2 electrons. And then the second one, dot and cross diagram, okay, from chlorine. Chlorine here, the chlorine Cl, as we studied yesterday, I told you that Cl has its own electronegativity and this Cl has its electronegativity also. So both of them, the electronegativity will eliminate each other. Therefore, this one Cl2 will be non-polar. This is the correct diagram how to draw Cl2. Cl with Cl. 1 dot 1 cross. And then for the NH3 ammonia, here ammonia, there are 3 bond pairs and 1 lone pair. 3 bond pairs and 1 lone pair as we studied last time about this one VSEPR. VSEPR is valence shell electron pair repulsion, and then in this one 3 bond pair and 1 lone pair. What is the value? What is the angle and what is the shapes? And then we have to check with the reference. What is the reference? The reference is the textbook on yesterday's presentation. Yesterday I already gave a presentation that the 3 bond pair with 3 bond pair and also 1 lone pair. This one, where is the 1 lone pair? Here. and then 3 bond pair nitrogen with hydrogen. So 3 bond pair and 1 lone pair. It is trigonal pyramidal. The angle is 107 degrees. This one, CH4 methane, there are 4 bond pairs here. Carbon bonded to 4 different hydrogen atoms, covalently bonded. So this one, the central, has 4 bond pairs, no lone pairs. 4 bond pairs, no lone pairs, the shape is tetrahedral. The bond angle is 109.5 degrees. And then let's see here. Aluminium chloride. Aluminium chloride. Aluminium, we know it is a metal, but it is not a pure metal. So aluminum chloride, it has 3 electrons in the outermost shell. It has the covalent character. So we can draw a LCl3 like this. This one, 3 bond pair without any lone pairs. So the shape of this one, LCl3, is trigonal planar with the angle 120 degrees. And then for CO2 like this, there is a double bond here. There is a bond. There's double bond here. Why double bond? Because there is one XO refer to one single bond. There are 2 XOs here. So meaning it is double bond. On the right hand side also there is a double bond. So there are 2 double bonds. When there are 2 double bonds, these bonds similar to single bond. Why single bond? Because this one double bond occurs in the overlapping orbitals of S and P orbitals of the same atom. Because the overlapping occurs with the same atom, so this overlapping we can count as one bond. It looks like that it has one bond. Okay, so the shape of this molecule is a linear 180 degrees. And then this one, next, H2O, water. H2O consisting of 2 hydrogen and 1 oxygen atom. Oxygen here, let's see the central atom, there are 2 lone pairs and there are 2 bond pairs. When there are 2 lone pairs and 2 bond pairs, so the shape of the molecule is bent with an angle 104.5 degrees. So this is the discussion of the yesterday's homework. This one I will attach on the Google Classroom. The mark scheme. Okay. So after this we are going to have more discussion on different topics.
Okay, students, that was about the discussion from yesterday's homework. Okay, from yesterday's homework, and then after this, I'm going to give an explanation about hybridization and also hybridization and intermolecular forces. The hybridization and intermolecular forces are written on your textbook, page 67 until finish of the chapter 3. So this is the theory of the
Today, I'm going to explain
completion
about
completion of the completion of the chapter 3. Okay, so I need you to pay attention on this.
Today, I'm going to explain about hybridization and intermolecular forces. Yesterday, we already learned about electronegativity. Let me revise a bit of electronegativity. Electronegativity is the ability of an atom to gain electron. So from the trend of electronegativity in the periodic table, from left to the right increases, from top to the bottom in the periodic table along down the group, it is decreasing. Why decreasing? Because the outermost electron will have greater shielding and less nuclear charge. Less nuclear charge means the attraction between the proton and the outermost electron decreases. Shielding means the inner electron, the inertial of electron prevents the outermost shell of electron to feel the attraction. So the electronegativity down the group decreases. Then across the period increases because across the period, the number of electron increases in a shell, in an electron in an outermost shell of electron. The number of electron increases. That makes the shielding across the period to be the same, but the nuclear charge increases because the number of protons more and the number of electrons also more, so there is more attraction. Okay, next, now this is about hybridization, hybridized and intermolecular forces. Hybridization we already learned in chapter 2, SPDF, electronic configuration, sublevel subshell electronic configuration. So unhybridized is like this one. This is a 2px orbital. This is an s orbital. Why px? We know that in p orbital there are three: px, py, and pz. This is an s orbital, and then when they meet bond, there is an overlap. Why overlap? Because they are showing that they are sharing electrons, and then that gives like this. The shape is almost same, which is not what we want, and also not they behave. And then this one, when hybridized, an sp3 hybridized orbital. So the p here the px is ready to make the overlap with an s orbital, and then there is an s orbital make an overlap. This is a better overlap. Why? Because the p has higher energy than the s, so the p shape is bigger the loop is bigger than the s orbital. And then this one that gives the s goes inside sp3 orbital. And then from here we can see that this one, the sp3 is distorted. The shape is getting bigger and being oval. Next, in hybridization there are three. One, sp3, second sp2, and the last is sp. sp3 occurs with a single bond. This is the ground state of carbon. Ground state is the standard based on the energy level that we do the atomic configuration. So the atomic configuration of carbon is 1s2, 2s2, 2p2. There are 6 electrons in the carbon. So the outermost contain 4 electrons. And then this one is 2p2. Okay. In order to hybridize, there is an energy. Electron. Electron contains energy. When there is an electron from other element, this carbon will be excited in excited state. Excited state, so it is called as hybridized. Hybridized become sp3. There are 3 px, py, pz. sp3. Okay. And then sp2. sp2 occurs in double bond. This is a ground state. Okay, ground state of carbon. And then when this one excited of carbon, 2, it is in sp3. Okay. And then how about in double bond? In double bond, there is a sigma bond and there is a pi bond. Pi bond occurs when there is an overlap of p orbital. This one. This is the sp2. Okay. So this is the sp2 here. sp2 ds with p2. Okay. So there are two, and then this one, this p orbital will overlap with another p orbital of another element. That is forming the second bond, or called as the double bond. Next, sp hybridization. sp hybridization occurs with triple bond. This is, I mentioned again, the ground state of carbon. And then the electronic configuration of the excited state. This is sp3. And then what happens with the triple bond? The first bond is always a sigma bond. The second and the third are pi bonds. What are those pi bonds? This one. The two unhybridized orbitals. This one is sp. No wonder in triple bond, there like carbon triple bond only can occupied by one hydrogen. The other bonds, the other three, occupied with electrons from the other carbon in carbon-carbon triple bond. Okay, so this one in the so let me summarize for the sp3, sp2, and sp3 occurs with single bond. Single covalent bond is always sp3. Double covalent bond is sp2. Triple covalent bond is sp. Now about ethene and ethyl. We know ethene contains double bond, and then ethyl contains triple bond. As I said before, triple bond sp hybridization, double bond sp2 hybridization. Okay, what is happening during hybridization? There is an excited state of electron. The atom in the orbitals get excited, so it is make its own arrangement to make itself ready to receive electron from other atom. Now the localized pi bond, it is with the structure of benzene. Benzene having the structure of three double bonds, not triple bond, three double bonds. So double bond is located over here, here, and here. Because in this structure, scientists have difficulty to name which one is carbon atom number one, because it is in the form of ring. So difficult to determine which one carbon atom number one. Carbon atom number one can start from anywhere of the carbon atom, but there are 6 carbon atoms form a ring. Because it forms a ring, so the structure can be made into like this. Okay, and then also this is called as the skeletal formula of the benzene. There are 3 double bonds. Because double bond can rotate in any position, that's why it is in the form of ring. And then the shape, this one is planar. So look at this one. This is the double bond. This is double bond. This is double bond, which is the same as this one. Is there any difference? Any difference of the number of carbon atom and difference in number of hydrogen atoms? Of course not. They are the same. How to determine 1, 2, 3, 4, 5, 6? 1 can start from anywhere. That's why the double bond can place in any position within the structure. This is what it means by the localized. The double bond can move around. We draw like this. This is a ring structure on top and ring structure below. It does not mean there are 3 double bond. There are triple bond. No, it is this ring represent the overlap of p orbitals, because the p orbitals can move around the structure. That's why we draw it like this ring. It can move anywhere. Now the carboxylate ion, similar to benzene is having in ring structure. In this carboxylate, we know that it contains C double bond O and then C and then O. And then this O, because O are oxygen is an electronegative element. So this electronegative element we know from the presence of the lone pairs here. Lone pairs. So this one here forming, you see the dotted line. This is represents the overlapping of the p orbitals. And then with this one is overlap of the s orbital. So in here, this one, the blue one, must be one oxygen, one single bond. And this one, the green one, this one, double bond. Why? Because the lone pair over here is only one. And then with the double bond, with the although double bond or single bond, they have two. Okay, so this one two. Why? Because although single bond, there is a connected to hydrogen atom, and then so the electronegativity can rotate. That means that makes the shape is like this. So the pi bond can rotate within this shape only. So because the pi bond can rotate, so we make into this ring, into half ring structure. Okay, so the O can goes to C2 goes to O, and then O goes to C, then C goes to O again. Okay, so the pi bond. Next, this is the what it means. The electron can go here, and then this electron taken. See the double bond, single bond. It's not obvious which one is double bond, which one is single bond. Is the double bond on top, single bond below, or the other way around? It is the same. There must be single bond and double bond. The portion of double bond and single bond can be up and down and up. That makes this one in the form of a dotted line, the connectivity. Next. Now about intermolecular forces. Intermolecular forces are attractive forces between molecules. There are two terms, intermolecular forces and intramolecular forces. Intramolecular forces between the atoms. Intermolecular forces is between molecules. Intramolecular forces, we learned there are four: covalent, ionic, dative covalent, and metallic bonding. Dative covalent is in between covalent and ionic. It is not purely covalent, it is not purely ionic. It is dative covalent bonding, and there is a metallic bonding. So this is the description of the diagram of intermolecular forces and intramolecular. Intermolecular, between molecule, this is one molecule of HCl. One molecule of HCl. This one, intramolecular, is the attractive force between the atoms, hydrogen and chlorine. Intramolecular. Okay, so do not make mistake in understanding about intermolecular and intramolecular. And then types of intermolecular forces. There are three: instantaneous dipole forces, permanent dipole forces, and hydrogen bonding. These instantaneous dipole forces and permanent dipole forces, they can be called as van der Waals. Instantaneous dipole forces occurs with covalent bonding. It has simple molecular structure because it has low melting and boiling point. If it has low melting and boiling point, it is not attached to the polar, cannot dissolve in polar. So it is most likely to be non-polar. It has simple molecular structure, and then it as if it has a magnetic moment. So sometimes it can be attracted, sometimes if not. Depends on the electrons and shape of molecule. What does it mean? If more electrons, then the instantaneous dipole increases. If instantaneous dipole increases, the boiling and melting point increase. Also, similar to the shape of molecule, there is an area of close contact between in the molecule that effect to the instantaneous dipole forces of the molecule. And then permanent dipole forces is we know already dipole. Yesterday I told you already about dipole. Dipole is the end of a molecule. There is one end and the other end. Now permanent dipole, we know that an element can be classified as electronegative, can be classified as electropositive. This one in HCl is electropositive. Why? Because it has tendency to lose electron. The Cl has tendency to gain electron. That's why it is negative dipole. And then this one will make a permanent dipole. Permanent means there is a electronegativity difference in the structure. So this one HCl has electronegativity difference. So that makes the Cl attract to the H of the other HCl molecule. So the attraction is connected. That makes the boiling point of permanent dipole forces higher than instantaneous dipole forces. The object of the dipole force, instantaneous dipole forces, the example is iodine. And then also chlorine gas, chlorine with chlorine, fluorine with fluorine. They have no electronegativity. No, they do not have electronegativity difference. So they are instantaneous dipole. They have low melting and boiling point. Okay, and then the last of the intermolecular forces is hydrogen bonding. Hydrogen bonding is the easiest. Why? Because it is the strongest intermolecular forces. Hydrogen bonded to nitrogen, fluorine, and oxygen. Example: nitrogen gas. Example ammonia gas. Ammonia is having a hydrogen bonding intermolecular forces. It is polar. It can dissolve in water. Fluorine, HF, hydrogen fluoride. It is also hydrogen bonding. It dissolves in water. The last is oxygen. When hydrogen bonded to oxygen, it is water itself. So water is polar. Why water is polar? Because it has hydrogen bonding. Polar can dissolve in polar, non-polar can dissolve in non-polar, non-polar cannot dissolve in polar, polar cannot dissolve in non-polar. Okay, so today we are studying about intermolecular forces and also hybridization.
Okay, students, so I already explained about two things. First was about the homework, yesterday's homework, and then for hybridization and also intermolecular forces. Until here, is there any question? Yes, Saka, you want to ask question? You raise your hand. I'm waiting for question from Nia.
I don't have any question.
Okay, today I also give homework on Google Classroom. So I expect you to do it and turn it on Google Classroom. Okay. The homework is to help you to get more understanding about this chapter. Is there any question? The material, the material for the presentation today that I did also on the Google Classroom already. So you can get all the information from the Google Classroom. Okay, let me take attendance before the class ends. So let me take attendance of 11P. Alicia is absent, Alberto is absent, Andrew is absent, Atta present, Billy was here, Billy absent, and then Brian is here, Carlton is here, Eiffel absent, Hayato present, Janice absent, Kyla absent, and then Kevin P absent. Yesterday he already gave the permission, asked for permission. Kevin N absent. Mario is absent. Matthew Dharma is absent. And then Maximilian was here, but he left. And then Natania is here. Saka present. Rizky absent. Sarah present. Shannon absent. Valentino present. Okay, so all this already. So if do not have any question, you may log out and we can discuss again tomorrow. Good morning, students.